Yeah, I guess we can wait a few minutes since we changed the room. So we are happy to accommodate 5 more students. We rejected 10 more. We couldn't accept everyone to join the class because we have limited capacity here. I appreciate that everyone wants to take the course, but we only accept those who are close to graduation, just as a way of helping them taking more courses. So hopefully we will continue with this course for the next semesters, so you can join, or your colleague basically can join in the next semesters. Should we turn off these slides? Can you see the slides clearly? Can you hear me? Okay. I think this hall is much better than the previous one. I can see all the faces. So we extended the deadline for the assignment. We got some requests. So please attend to that. It will be very difficult to extend more beyond that because we plan to start presentation around the 1st or the 2nd week of October. So the first group will have about a month to prepare for the slides, which is something not pleasant, I believe. But we will do our best to accommodate that. We will try our help to give them 2 weeks to prepare the draft, and then we will have a meeting with them, try to improve their slides, and we will consider that they had only about 3-4 weeks to prepare for the talk. You consider that in the grading, so you don't have to worry about that. Okay? We will try to fix the schedule ourselves. We will set the dates and everything, who's going to present first and who's going to present next. And then we will post it to everyone. Only those who cannot meet it in the particular day can send a request and we can do swap. Okay? But we will try to cluster all these papers based on the topic. So it makes more sense to have 2 talks that are relevant in the same day. Okay? This is the only criteria we will be using. But we will try our best to shift the block, 2 talks together, to shift them to different weeks. Okay? I guess we can start. I can hear myself. Okay, I already muted here. Or probably better if I muted the other side, so I can hear if someone have questions. All right. So welcome to the 3rd lecture. Last time we discussed about how to analyze, how to present research papers. Hopefully it was fruitful. You get some new information, new details, and you will exploit all these on your talk. So this is very important to really improve yourself, improve your skills, improve your slides. If I see some of those aspects missing in your talk, I will feel really not good. Okay? Especially the things that we emphasize several times, at least slide number. I really need everyone to include slide number in their presentation. Okay? Before we start, yesterday was a holiday. Happy Labor Day. So happy Labor Day to your parents, to yourself, and to everyone. We know how hard people are working, try to make a life, right? So how many of you know where this picture was taken? or what is about? Is it AI generated? Okay, yes. Who else say AI generated? How many of you? Raise your hand, please. 1, 2, 3, 4. Okay, about 15. Say yes. This could be like AI improved, okay, increasing the quality, given it was black and white, but it's a true picture. Okay. This was taken on the 69th floor of this building. This building in New York called 30 Rock. And you can see something funny about the workers. First, there's no safety measure at all, right? Second thing, you can see some of them are drinking. Some of them even smoking, right? At that high. So this is very important to take safety measure when you start working. But at least they are keeping their smile. And this is what matters. Life is very difficult these days. So please relax, keep smiling, and everything will be moving. All right. So last time we discussed about how we can talk to the computers, right? How they can understand us. So basically, we want to develop something, a method of solving a problem. We call it an algorithm, right? Which is something descriptive, something we understand as a human. We convert that algorithm into a piece of code, which is programming language. We use certain instruction on how we can write those lines or piece of code, right? And this is usually human readable still. At least we can read the for loop, the plus sign, the equal sign, all those math operations. However, computers do not understand this language, right? We have to go a bit lower in the level, closer to the CPU, convert into what we call assembly code. In assembly code, you can see not all human can read it. You have to be really expert in this instruction to understand what's happening. Yeah, you can maybe guess what is add, but maybe you cannot guess what is next. SLL. If you ask your brother, for example, what's SLL, probably won't know. Okay. And you can see we specify those variables exactly, the values to be added. We really, as we are talking to children, right? Start to give them the information as a ready and piece by piece, right? Now, still, this one, computers cannot understand it. And we need something at the lowest level, which we call machine code. Machine codes, just 1 and 0s, where we really tell every single transistor what's happening. We tell the logic gates in the computer whether to be enabled, disabled, activated, whether to do this type of instruction or computation or something else. Now, we discussed this last time very briefly, just touching the surface. This is the CPU. Okay? There are main steps in the CPU. We are going to visit them probably in the next week or the one after, and we will discuss how we can improve the CPU. So let's keep it aside. For today, we're going to focus only on the memory system. And this is really an important topic in today's computers, given the workload that we are dealing with, especially with artificial intelligence. So the number of parameters are increasing, and that is a huge challenge for modern computers, how they can deal with the LLMs. What is a computer memory? Storage device. Excellent. So we use those devices to store data, right? But not only to store, also to load, right? We store something, we want to be able to fetch it back or to get it back, okay? And it's not only data, we have also instructions. So any program is basically instructions and data, right? This is AI generated, as you can guess. It's really not near what we have. It's not really true. So this picture does not mimic what we have in DRAMs, for example. Something really futuristic. All right, so what is the need for memory? First of all, we didn't have any need to store or load these data. But with the advancement in the CPU, the hardware resources provisioned in the CPU need the right data at the right time. And that is the source of the problem, that the CPU really need some place to have all the data. And then because it's very fast, it can take all of them piece by piece quickly. If those data are not ready, then most of the time the CPU is just stalled, just waiting for data, doing nothing, right? And that is the source of the problem. So the problem is that the CPU is really fast. Programmers want unlimited amount of memory with low latency. What does it mean? Always when you program something in C, you want to have an array, right? Sometimes you give it a fixed size. Sometimes you give it unlimited size, right? And you want it to be as much as possible to be a bigger size, right? And that will benefit your program. However, you might run out of memory quickly because you consume that much of memory, right? And also, you don't want to have a data that's very slow, especially when updating the record and when getting back those data. The problem that fast memory, we do have them. However, it's more expensive per bit than slower memory. This is telling you that we have two types of memory. One of them is very fast, and one of them is very slow. Okay, so why not just using the fast memory? Why do we care about the slow memory? Which one? The fast memory is very expensive. That's one, right? And this is very important. Who's going to afford a $10,000 machine, right? Will you buy it? How about 100,000? Nobody will buy it. So the price is very important metric here. As a computer architect, you have to worry about that, right? It's not only the performance. What we have here is a plot. Maybe we can hide. This is better. So this is processor versus memory performance gap. As you can see, we have here in the x-axis the years, right, over time, and we have in the y-axis the performance. And performance is different between the CPU and the memory. What we have in the CPU is instructions. How many instructions you could process in a cycle, right, or in a second. In the memory, how many transactions you can do between the memory device and the outside or the off chip. How many requests, read and write requests you could satisfy, right? So around that point, we almost have equal performance between the memory and the CPU because the CPU was really slow. Why is that? Why the old computer were slow? What is this? Transistor, right? What's the problem with the transistor in the old days? The size was huge. The size was huge. Or what we call as technology node. The technology node, currently we are talking about 1.5 nanosecond, right? This is of the channel here in the transistor. This is the least we could achieve, or maybe we could have more advanced technology, which I'm not aware of. Okay, but in the old days, we were having something even in micro, not in nano. Okay, something really big, something really huge. And as we go over time, we keep shrinking the transistor size so we could fit more transistor per chip. More transistor per piece of silicon means faster performance because we could compute more things in the same second, right? Because we have parallel ability to process things, right? So as we move over time, the performance of those transistor or the processors getting better, even much better than what we have in the memory. So as you can see here, the performance improved or doubled almost every 18 months, which we call Moore's law, right? So Moore's law predicted that in very old days, that we are going to have all those processes doubled in performance every 18 months or year and a half. When we look to the memory, it's doubling every 10 years. Every 10 years. What happened here? Why the performance almost saturated? What happened with the processors? At some point, Intel stopped scaling the transistor side. We were having a lot of challenges to fit more transistor per piece of silicon. Okay, yeah, we reached 1.5 nanosecond, but then the technology cannot deal with more. We cannot shrink more. What will happen after that? Okay, almost they are connected to each other, all the transistors. So you cannot differentiate between ones and zero. Which one is active, which one is not active, right? So they start as a workaround to have 3D structure, for example. So they fabricate those transistors in 3D shape, and they stack them vertically rather than lay them out in the horizontal surface. But for some time, that stayed the issue. So the performance of those processors saturated over the time, and then we could increase only the number of cores rather than improving the core itself. But still, as we move over time, the performance remains very critical, that we have a processor or CPU is very fast and the memory very slow. How we should deal with that? This is Moore's law. How many of you know this guy? He died 2 years ago. He was one of the co-founder of Intel, and he was working on this thing about 1959. He predicted that all these CPUs will continue in doubling in terms of number of transistors. So this is very famous prediction, and this is really was a truth. So he predicted almost 70 years ago, and it was really true over that time. Okay? However, he said, as we move over time, the price you pay, or the manufacturing price for adding more transistor, will drop over time, okay, because technology improves, things getting better, and you could increase the number of transistor dramatically from year to year until you reach a point that you cannot fit more transistor. And then the cost of that transistor or the chip will start increasing after some point. So you cannot really having unlimited number of transistor per chip. So you could fit more, yeah, as the technology node shrinks or getting better. You could add a lot of transistor, making the core operating in a very fast speed up to some point. After that, you cannot do it. You need really much larger wafer to include all these transistors. And for that, the price will start increasing. So you have to stop at some point adding more transistors. All right, this is another plot. This is for the processor and memory, also about the performance gap. But we can see here that the problem persists also for the GPUs. So you can see here multiple of, this is a computer, right? These two computers now start having a GPU from NVIDIA. We start having AI engine, the A100, the H100, and so on. All of them scaling very well in terms of the performance. As we grow in time, we start getting all those advanced technologies. But with the problem with the memory, even with the most advanced one, the DDR5 and the HBM, high bandwidth memory, those are the latest technology in 3D stacking the DRAM. So instead of having the legacy or traditional DRAM that you have in your computer, we start having those what we call 3D stacked memory, or HBM, high bandwidth memories. In most GPUs, the latest one and the FPGAs, we have them. We don't have the DRAM, okay? We have the HBM, which is in fact DRAM, but stacked in a 3D structure on top of each other. So the memory wall remained there, okay, even with the latest, because the previous figure was up to 2005, I think. Not only that, now even with the very recent years, things happening this year, we can see the memory capacity almost is not scaling well. The increment is not even 1.5 over from year to year. However, the workload that we are dealing with on daily basis is getting huge. We have more than exponential growth in the number of parameters that we are dealing with. So almost the transformer size is increasing by 240x almost every 2 years. All right. So yeah, now hopefully I convince you that there is a real problem between the memory performance and the CPU performance, and that persists until today. Okay? The solution is very simple. However, it might not be effective today. So this solution was proposed in 1945, and it was used until maybe 2-3 years ago. Okay? All computers rely on this solution. And let's see what is it. So the solution is simple. Organize memory system into hierarchy. Okay? You cannot bring fast memory because it's very expensive. You cannot make the entire DRAM as fast memory. So let's keep the DRAM, the very slow one. Let's have it, right? And let's bring more faster, more advanced memory with less capacity. How many of them we need? We need a hierarchy. The number is not fixed. It's up to you. So the entire addressable memory space available in largest, slowest memory, which is the DRAM. So all computers will have that DRAM still there. Incrementally smaller and faster memories, each containing a subset of the memory below it, proceed in steps up toward the processor. What does it mean? So we have the DRAM very far from the CPU. We have the CPU. And in between, you can control the architecture. You can do whatever you want. What we call this model, the Neumann model. The Neumann model. This is a very important name in the computer architecture because everyone is using it until today. The Neumann is an American scientist who was the first to develop a memory for computers, the old computer. You can see it's a room-sized computer. The problem with these computers, you turn them on, and then you handle a lot of vacuum tubes to insert the value, 1 and 0, right? So if you want to do a mathematical equation, just 1 plus 1, what you would do? You need to set a lot of those controller, right, until you get the result. Now you want to do very long equation, like for NASA. So you spend 1 week inserting all these values, adjusting the equation, the type of operation, and so on. And then you get the calculation. Then you turn off the computer. What will happen? You lost everything, right? Next time you want to apply the equation, you repeat the entire step. You set all this vacuum tube to be 1 and 0, 0, 0, 1, 1, and so on, right? And so on. Then he said, okay, this sounds crazy. Let's just have a simple memory where we store the program that we are going to execute, which is basically equations, right? That's why we call it as the first stored program computer. And the concept was simple. Let's separate the CPU or the processor from the memory. Let's have a memory device and we have a CPU. And basically we have the storage, which is volatile or non-volatile. When you turn off your computer, do you lose your data on the hard drive? No, which means it's non-volatile. Okay. However, what we have in the DRAM is volatile. Okay, what does it mean? Once we turn off the computer, everything will go for good. No more there. As we move over time, we start having more complex than that concept. We no longer have single memory. We have a lot of these type of memories. We have a lot of these type of surge. And even the CPU is no longer a CPU. We have a GPU inside it, embedded inside the CPU, right? We have a GPU to replace the CPU. We have even FPGA. We have custom-made processor, no longer general purpose, right? So all the things start getting more complex. Now let's see the hierarchy. We already talked about the hierarchy as a workaround, as a solution, because the memory is very slow, the CPU is very fast. What is a cache? The cache memory speeds up processing by temporarily storing instructions and data that the processor is likely to use frequently. Why likely? Why likely to use frequently? Why not just moving the data that the CPU will need? What is that? The loop? Why we move the data that is likely to be used? So there is certain probability that those data will not be used, right? That's why we say likely. Why is that? Excellent. Do you understand what he said? So it takes a lot of time to bring data from the main memory. So rather than having a lot of round trip going back and forth between the memory, bringing data, go back to the CPU, we bring a whole pile of data, a certain amount of data, including the things that we need and the things that we may not need, but we are going to need very soon, right? There's a probability that we will need it soon. So we bring all those data to the CPU. We will take the part that we need, and we keep the part that we don't need. Hopefully, in the very near soon, we're going to use it, okay? Oh, sorry. Sorry. All right. So generally, we always store some data here in hopes that it will be used in the future. And we save ourselves the distance time it takes to go to RAM, okay? Now, we already remember, how many of you remember this picture? We already discussed in the first lecture. How many of you remember? What is it? So we start with the algorithm, implement it, programming language, store it in the hard drive. Every time we turn on the computer, we move the things from hard drive gradually to the RAM, main memory, to the caches, all the way to the CPU. What are similar analogies to the caches? What could be a real life story where you save really going back and forth instead of going every time, bring something, come back, bring something, come back? What you would do? What could be very similar analogy to this, or a story that you use in real life? Yes, please. DNS server. What we would do? What is similar to cache? Raise your voice, please. Excellent. You could have the microphone Hopefully in YouTube, people can hear the answer. I have another microphone. Could have it for the other question. I'm going to lose weight in this class. Okay. Excellent. So this is similar to DNS. What is DNS? Domain name server. What it means. The name that you type, www.something.com, it's not actually that. What you actually type is the IP address, right? And how we know the translation between those names, the full name and the IP address. We need a lookup table where we store all this information and how to detour between different servers around the world, right? And instead of going all the time to the server in the US to visit a website coming from the US, you store it somewhere in the way, right? And you check if it's there, you got it. If it's not there, you go back to the original source, you fetch it. Next time someone requests the same website, done. You don't have to go all over the round trip, right? That's an excellent example. What I have for you, something that you use on a daily basis. Something exists in all kitchens, right? How is it? This is the algorithm. You call your mom back home. I want to do something. I want to cook. What is this dish? Come on. And how you do it? How you do butter chicken? You got the recipe from your mom. That's the code, right? So over here, something human readable, but over here, it's clear instruction. Bring this, do this, cut this, cook this, right? You bring that recipe, and what you have in the secondary storage is basically your fridge. It has a lot of ingredients, not only the ingredients that you need, right? And even if you close the door, you open the door, it doesn't matter. The ingredients will remain there, right? This is as secondary storage. Why? Because you have all type of data, the things you need, the things that you don't need, the things you might not need at all for next 100 years, right? And exactly with the ingredients in the fridge. To cook this dish, you might not need everything in there. You just take out the ingredients that you might need, you put it in countertop, which is the DRAM, right? You start processing gradually the things. So you bring only vegetables, you start washing them, and then slicing them, and so on. And you do that to all the ingredients in the countertop. And this was a perfect example how to mimic or visualize the process that's happening in the CPU. Hopefully by giving you a lot of these examples, so you never forget this story, okay? All right, so we said as a workaround, let's have the hierarchy, but we didn't explain why. We want fast and large memory, right? That's one. But we cannot achieve both because fast is expensive and the large memory is also expensive but slow. So those requirements contradict each other. The idea is to have multiple levels of those storage to achieve two things: temporal and spatial locality. Temporal and spatial locality. What does it mean? What do we mean by temporal locality? So temporal locality from time, right? So what do we mean by that? The same memory location will likely be accessed again soon, okay? So it's related to time. So we might need it in very soon. That's why we need to fetch another block to achieve the temporal locality. For spatial locality, the nearby location will likely be accessed soon. The nearby location, not the location we fetch. That is something close to where we fetch. So we already got a block, but maybe the surrounding blocks might also be needed in the very soon. Hopefully you remember this picture from the first lecture. We always will have the CPU. Those things are not fixed. Those things really not fixed, right? We could have L1 only. Could have L1 and L2 only. We could have L3. We could even have more. Okay, we will see a few examples of that. After all these level of caches, we will have the RAM. This technology used in the cache is different than the technology used in the RAM. Okay, so it's not just smaller memory. It's not like the same as the DRAM, but we have it at smaller capacity. It's totally different technology. The technology we use over here is, what is the building component of the DRAM? What is made of? The DRAM you have in all your computers, what is made of? Capacitors. What else? The capacitor is a device to store a charge, right? We can store like 5 volt, 1 volt, and so on. However, if we want to discharge or charge it, we need a controller, kind of a controller, right? Which is a transistor. So we always have transistor and capacitor in the DRAM. But what we have in the caches, we have transistor, excellent. But what to build up out of that transistor? We have 4 to 6 transistors to make D flip-flop, which is kind of sequential gate, not logic gates. D flip-flop. What is a D flip-flop? It's also a gate to store a value, right? You can store value over there. Okay, so the technology made in the caches is really different from the technology we use in the DRAM. That's why here are very fast but very expensive, and this is very slow but can have like higher capacity. All right. So let's look at this abstraction, and this is what you really see when you program something. When you request, I want a 10 gigabytes of memory, what will happen? And your main memory is just 1 gigabyte. What will happen? Now the concept of virtual memory and physical memory. The physical memory is what you really have. Okay, you have 1 terabyte of storage as hard drive. Okay, but what you virtually have could be something more. Why? What you see is only the virtual memory, and you always look at it as infinite memory, right? You don't know in advance the memory until you check the properties or the specification of your computer, and then you request that amount of memory, and then when you run your code, you figure out that's out of memory, okay? Or you get an error. But in reality, the physical memory size is much smaller than what the programmers assume, which is the main memory, right? The main memory is 1 gig, but you are requesting 10 gig of bytes. And how that's possible? How you could request more than the main memory? In fact, you don't have to worry about that. You don't have to implement anything to do that. The operating system will know exactly the amount of memory that you actually have, the physical memory, right? And you try to map whatever you have in the main memory to fit pieces of what you need. So you can gradually bring from the storage, do some process, store it back to the storage, and get more, do some processes, solve everything, and store back all these results, right? So that's why we don't worry about how you manage, how you move all these data from the hard drive to the main memory to the caches. That's because of the concept of virtual and physical memory. And who's handling that? The OS, the operating system. You don't have really to worry about anything related to the moving the data. And that's really invisible to the programmer, okay? Or transparent. Programmer doesn't need to know the physical size of the memory nor manage it. And this is a very important aspect because it makes your life much easier. You don't really have to worry about the architecture underlying your program. What could be an ideal memory? If I'm going to purchase one memory from the market, what should I be looking for as ideal scenario, which is not necessarily to be realistic? The first thing, 0 access time. The latency, I want it to be 0 or minimal. Why? Why is that important? Every time I move data, I have to wait a lot to get that data back to the CPU. And we are going to see how a lot means, okay, the exact time to fetch all these data. Infinite capacity. The larger, the better. What is the size of your DRAM, for example, in your laptop currently? 24 gigabytes, right? How about you? What is the size of your DRAM? Can you check? Very easy. Go to the Apple logo, go to info. Yeah, everyone, please do it. Can you tell me numbers? 16, 16, 20, 12, really? Should be multiple of 2. Okay, yeah. So the larger, the better, right? The larger, the better. Why is that? Again, it's about how much you can put in the middle of the way. Instead of going all the way back to the hard drive to bring the data, if you have something to shorter that for you, that was something very fast. This will make a lot of sense when you are dealing with memory-intensive applications. What does it mean? This term is really important, and you see it a lot in most of the papers that you are going to present. Memory-intensive application. What does it mean? It means applications that are hungry for data. They're always visiting the memory to bring more data. They do small processes, small CPU computation, but most of the time they're bringing data. This is similar to which real-life application? How many of you are dealing with memory-intensive application? Just give me an example. Something all the time you bring a lot of data to visualize and start seeing different things on the screen. Games, for example, right? So in games, what's happening, once you move from the X and Y, from one point to another point, you start drawing or rendering or visualizing a room, right? As you move forward, you start getting more scenes, right? You move this side, another scene is happening, rendered on the screen, right? You keep moving in all sides, and all sides you get something rendered differently. And this amount of data is huge, tremendous. Every time you just move your head, something else is being drawn, right? And that is a memory-intensive application. That's apart from AI application, for example, where you have a lot of parameters you need to get inference for. You also need a minimal cost, right? An infinite bandwidth. What's the difference between the bandwidth and latency? Speed versus time, okay? So the bandwidth, what is the amount of data you could move in 1 second, for example, okay? And zero energy. Energy is really important here. All of these requirements really opposing each other. All of them. For example, as we said many times, the bigger one is slower. The faster is more expensive. So how I can really be in line with all of these requirements? Higher bandwidth is more expensive. Let's see a realistic example. Those are true numbers. Let me know if you cannot read these numbers over here. This is very important. I can maybe try to zoom in. Let's see. Can you see now? Okay. What do we have here? We have a CPU. What is inside it? We do have some small number of registers. Registers are also memory, right? We can store something quickly, and it will be near all these ALU, or arithmetic logical unit, okay, where we do the computation. However, this is very small, very minimal memory, so we cannot rely on it. To read something, this amount of data we could accommodate over there, it's about 1 kilobyte. 1 kilobyte, something very small, okay? And this is very good to hold the intermediate variables. Once we do addition, for example, we add one variable to another variable, we got a result, right? This result will be stored in one of these registers until we move it to somewhere else, to the cache, and then we store it back to the hard drive. The time needed to read these registers is less than 1 nanosecond. Something very small, very quick. And to make sense, because it's near to the ALU. Now, once we move to the L1 cache, and L1 cache, remember from the picture we just showed, it's inside the CPU. It's not off chip. It's not outside the CPU. It's already inside. Now, the amount of data we can store, 64 kilobytes, which is 64 times larger than what we have in the register, right? And as you can guess, the time to access the L1 cache and get data is about 1 nanosecond. So now we were talking about less than 1 nanosecond. Now we are in multiple of nanoseconds, right? Once we move to L2 cache, what we expect to have larger capacity. However, we are moving in the trip. So the execution time or the round trip to visit and come back to the CPU now become longer. So we have about 256 kilobytes, and the time needed to visit the L2 cache about 3 to 10 nanoseconds. Now, why those numbers are important? As computer architects or as people who study advanced computer architecture, why these numbers really matter to you? 1 nano, 2 nano, 10 nano, it's still less than 1 second, very small. Now, we talk about memory-intensive application, right? But there are too many other applications that require a lot of execution. But not only that, when you run the computer, you normally don't run one application. And I bet all of you have now maybe more than 10 applications open in your laptop, right? Including Chrome, maybe more browsers, maybe the PowerPoint, maybe video recorder, maybe some of you playing games. Who's playing games? Anyone playing games? No? Right? So you have too many applications already open in your laptop, and all of them running for the CPU, trying to compete to get executed, right? So every single fraction of time different between these steps is really a big thing. Now, once we move to L3 cache, the nice thing is always shared between multiple cores. So in the CPU, normally we don't have single core, right? We have different cores. The L1 cache normally is dedicated to single core. So each of these cores have its own L1 cache, right? Intermediate memory. Don't forget that we have registers inside, right? Now, the L2 cache normally either has dedicated one, like each core has its own L2 cache, or shared between two cores, for example, okay? Now, we also have L3 cache. And the nice thing about the L3 cache, that is shared between all the cores. So all of them access the same L3 cache. Why? Because something huge, right? And the data we move, normally, it's really not relevant to one core. So we bring a lot of data that might be needed very soon. So it makes sense that this core also access it and bring whatever its future and try to process it. This core is already processing the current data. This one is processing the future data. And this is how you achieve like fast performance. Now, when we move to the main memory, you can see we start dealing with the numbers that you just mentioned, 16 gig, 32, and so on, right? But the time to visit the main memory, it's somewhere between 50 to 100 nanoseconds. 100 nanoseconds. So we were talking about inside the CPU less than 1 nanosecond, right? Now we need to pay 100x more time to visit the main memory. And imagine every time we need data, we pay 100 nanoseconds, And not only that, not only 100 nanosecond, because we need to bring the data to where? To L3, right? And then to L2, and then to L1, all the way to the CPU. So you can imagine how expensive to pay that cost. Hopefully those numbers give you an idea how expensive is just to bring one piece of data. And normally your program needing like 10 gig, 5 gig of data, right? It's not 1 byte. All right, now let's jump more with the numbers. So hopefully it can give you a realistic example of the challenges that we are facing. How many of you know i7 core? Intel i7 core? Almost everyone, right? This is popular, although there is i9, the latest, but the i7 is more popular. The i7 core can generate 2 references per core per clock. What does it mean? Every core, this is a core, right? This is a core, this is a core, and this is a core. So every core is generating 2 references per clock. What are references? No, the thread is different concept. So those references are requests to the memory. Give me data. So it could be read, it could be write. Okay? So it could be read, or it could be write, or it could be 2 read requests, for example. I want to read 2 variable or 2 block or 2 pieces of data to that core. And each core can do that in single clock cycle. In single clock cycle. How slow, how fast 1 clock cycle? How we could know what is the time period for 1 clock cycle? You already know this, right? What is this shape? 0101, yeah, or 1010. But what is it? Periodic signal, excellent. And we start having a frequency or something frequent, right? Which one is frequent? The things between the lines. Not this one, not the peak. This is not frequent, right? Because we have ups and then downs, up and down, up and down. So what is frequent here is the up and down together. So this entire thing, we call it a time period because it's frequent over and over and over. So this time period is what? How we measure it in the computer. This is 1 clock period. And in time, how we measure it? 1 over frequency. 1 over frequency will give you the time period for this frequency, right? So if I want to know, given that the frequency, I already have the frequency. Thank you. I want to know the time period used to generate these 2 requests per core. What could be? So in i7, we have about 3.2 gigahertz. That is frequency. So 1 over that number, 3.2 gigahertz, will give you the time period over there, which is normally in nanosecond, since we have gigahertz, right? 1 over gigahertz will give you nanosecond, something like that. So this is how we figure out the time period for that. And you can check, all of you, your laptop, you can see the frequency of your processor. So you can do that. 1 over that number will give you the time period, and that time period is the amount of time for the core to issue those 2 references. What does that mean? It means we have about 25 billion data references per second, okay? Because we have 2 references. In that time, we'll give you that much amount of references per second. Now that is translated into 409 gigabytes per second. Let's compare it with the memory. The best memory you have, probably all of you have DDR4, what we call DDR4. DD. which is double rate DRAM, right? With the standard 4. Okay. Now, currently in the market, we have DDR5. This is the latest. Most of the PC probably you have DRAM 4. The bandwidth for this DRAM is about 34 gigabytes per second. And this is really how you can check the differences between the main memory in a practical way, between the main memory and the CPU you have. Now, you already know what kind of CPU you already have in your laptop, right? Probably it's Intel, AMD, or maybe Apple M4. How many of you have M4, M3, M2? Okay, we have a bunch. Yeah, so you can still check the frequency you currently have, right? And you can check the CPU. And from knowing the name of the CPU, you could know a lot of specs. For example, how many transactions or references per clock cycle, okay? How many cores do we have? And based on the core, how many caches do we have? Can we cope with that amount of memory or not? And this is really how computer architects, when they design one processor, they need to deal with all this amount of information. So it's not really just out of nowhere, I decide to have L2 cache of this much of size, or L1 cache this much of size. When we look into i9, for example, it's issuing 5 references, not 2. In the i7, we have 2 references. Now we have 5 references per clock and per core. Okay, those 5 references, 3 of them to load data and 2 of them to store. So it's amazing how a single core can really send 5 requests to the memory to get data. That's per single clock cycle. In the DRAM, we still have the scaling issue. So from DDR4 to DDR5, the bandwidth is not that much higher. So with the same capacity, you can see the increment is barely 4 gigabytes per second. Although we do have like higher capacity than this, but to do fair comparison, we have to compare that number with that number. So memory always not scaling well. You don't expect to have double bandwidth, for example, from 1 to 1, unless you purchase one with largest capacity. Of course, you will get higher bandwidth, right? Now, all the numbers we just saw, we just see together, right, in that plot, showing the L1 cache, the memory and time, L1, L2 cache, memory and time, and so on. That's for one processor. When we move to other processors, we will see these numbers totally different. For example, we can see caches of size 10 megabytes or more. Let's see an example of that. What is this? What is this? You know this logo? Yeah, this full self-driving processor for Tesla cars. Okay, full self-driving. That's why we have FSD chip induced in Tesla cars. Why do we have 2 pieces? Why redundant? Excellent. So we have redundancy to cover in case we fail, right? Why we have such thing? Remember, this is for self-driving cars. Imagine you are on the 400 driving in full speed, right? You want to catch the class, and then the car out of nowhere decides to stop. What will happen? All the car behind you, at least, will crash with you, or you'll go just hit something, right? So sometimes in some architecture or some application, we really need redundancy. If someone of them will fail, directly the other one being already calculated the same thing, so directly feed in with more input and data. Okay. Once we zoom in to single chip of those, what we will see? So we'll see, okay, there is CPU, GPU, there is NNA. What is NNA? Neural network accelerator. Excellent. So, okay, we have CPU and GPU. Those terms like sounds familiar. Okay, what's special in the architecture? You have neural network accelerator. Why is that? So this chip is built to see a lot of things in the cameras or sensors around the car, right? And then to make sense that all of those are implemented as machine learning model to detect quickly the things, the objects, and recognize them, whether this is the lane, should I switch to another lane, is there an object, and so on, how far, how close to the car, and so on. Now, what is special in the neural network accelerator, that each of those chips has two of them, two accelerator, okay? And each one of those accelerator has 32 megabyte on-chip SRAM cache. So there is single level of cache that is 32 megabyte, okay? That is for a single neural network accelerator. And then the chip itself has two caches. It's not hierarchy. Each one of them for single neural network architecture, okay? So you can see now the flexibility with playing with the hierarchy and how fast, how big you can go with those caches. You have any questions? Hopefully by the end of the lecture, we'll see a lot of those examples, real life example from different processors and what kind of caches we do have. As I said, the SRAM, do you remember what's made of? We just discussed it. D flip-flop. Who said that? D flip-flop, right? So DRAM is made of, oh, I'll check later. So the DRAM is made of capacitors and transistor. Don't forget that, capacitor and transistor, because capacitor is only able to charge, okay? But we need a controller to control when to charge, when to discharge. Charging means a voltage, which means a 1, a value of 1. If the capacitor is charged, then we already store a value of 1. If it's discharged, then it's a 0, right? And this is how we control 1 and 0. So we keep feeding the capacitor with voltage. It's charging with 1. This is how we store 1. Discharge it, then how it remain with 0. The same thing with D flip-flops. But D flip-flops could go with the smaller because we only controlled with transistor. It's not like bulky items as in capacitors, right? That's why we could go with very high speed. We only control by clock. Single clock cycle, you could activate the D flip-flop. That's it, okay?
So does that, I think you have two different SRAMs. Suggesting that they both are independent.
I'm not sure how they are connected, those accelerators, but probably, yeah. So it could be shared. I'm not sure if it is LLC. If it is written also LLC, then probably it's shared. Yeah, it says two independent instances. Probably they are separated. Okay.
Also, the label there, are they hardwired or?
That's a good question.
Like besides in the 4 point million.
Yeah, we can check. So I get this information from the PDF over here, so we can check that. But this is a good question, especially those who are interested in machine learning. This is very good how you build that architecture, how you make it faster. Okay, and also the question, why 32 megabytes? Why not less? Why not more? Right? So that is also about the workload characterization. So you already know that you have 10 sensors, for example, in Tesla car. How many of them working in the same time? And what kind of workload do you have? Do you store the entire video or only when you have differences between the frames, for example? What is the amount of data you have to be processed in the same moment, right? Because you process as you go. And even sometimes you predict that there is a car even ahead of 10 cars from you, right? All right. So now we already set the stage for caches. We explained a lot of things. Hopefully you never forget the story about the caches. This is a very important topic in interviews, right? You'll get a lot of questions asked about how you deal with DRAM and cache and the CPU. If there's a mess, what will happen? If there's a hit in the cache, what will happen? Why we have different level of caches and all these questions. It's very important to imagine the topic in your head and you be able to play with it, to design those numbers. Now let's see things related to allocation, how you allocate certain amount of memory in the cache itself, how you map the data from one component to another. Okay, I move the data from L3 to L2. Where to place it, right? Where to place it exactly in the cache. And once I have the cache is full of data and I need a new data to come in, what exactly need to be replaced with that new data? Okay, please remember this picture. This is very important. We are going to use it, I think, for the next 2-3 weeks. We have a lot of questions. We're going to answer them in the class on how we calculate the things related to miss rate and hit rate. Okay. Now, in a word, how many bytes in a word? 8, 16, 2. Who said 2? 16. Equal to byte. 16. 1 byte is a word. 4 bytes. 1 or 4? Okay, please check that at home and let me know the number. He is very close. Okay. All right. When a word is not found in the cache, then we call it a miss. And probably you already know that, right? But if it is found, we call it a hit. Fetch words from lower level in hierarchy requiring a higher latency. Why is that? When we say lower level, it means around the memory. When we say higher level, around the CPU. Higher latency because we already know these numbers, right? It just adds up. Also fetch the other word contained within a block takes advantage of spatial locality. Why is that? Because we already bring that block. So if you're already using some piece of information there, we need the other piece of information that's contained in the same block, then no need to visit any other part of the hierarchy. Now, something very important, and this is a metric used when we evaluate programs. If I ask you to write some program in C, and your friend write the same program in C, the other friend write a program in C also, how we could say this program is faster than the other? One way, just to run it in the same CPU and measure the execution time, memory requirement, maybe storage requirement, and so on, right? A program that's faster means better, right? However, internally, we would know what makes it faster. What makes it faster? One metric is to measure the miss rate. The miss rate. What does it mean? So the miss rate is a fraction of cache access that result in a miss. What does it mean? I have the CPU. I have the cache. I have one request. The CPU is asking for more data. The cache said, I don't have it. What do we say here? A miss, right? Okay, next time I ask for more, say a hit. What is the miss rate here? We have 2 requests. Please, people on this side, I need participants. We have now 2 requests. One of them is miss, one of them is hit. Then, what is the fraction of cache accesses that result in a miss? It's a 1 over the total number of requests, which is 2, and we get half as a miss rate. Which one is better, the larger or the smaller? The smaller, right? Which means we have low number of misses over total number of requests, which is better because the cache all the time have this data, which means the algorithm to bring the blocks from the main memory to the cache was successful. Some designers prefer measuring misses per instruction rather than misses per memory reference. What does it mean? Here, we don't care about instructions or what was the program about, right? We just measure in total how many of those misses over the total number of requests. However, it makes more sense to know what is the miss rate per instruction, okay? So we change a little bit our equation into this, which is misses over the number of instructions that you have in your program, for example, 10 lines. And remember, the instruction, when we say here, it's not the C code. It is assembly code. That's the thing we have in the CPU. Whenever we talk about CPU, it's no C code, no Java. Whatever you have, you convert into assembly code, and then machine language, which is equivalent to assembly code, but we just convert all those instructions to the equivalent 1 and 0s, right? But still the same number of instruction is there between the assembly and the machine code. And this is what we mean by instruction. So it equals the miss rate, which we have over here, the fraction of requests getting missed, right? Times the memory accesses, how many times we access the memory. For example, the miss rate is 1 over 2. It means 50% of the requests are being missed, times the total number of memory, for example, 100, 500, or 1,500, for example, right? Times this, over the instruction count. When you think about those terms, you'll see like it really makes sense. So you are dividing over the instruction count to take the average. What each instruction resulting in misses, right? On average. Because some instruction might result in a lot of misses, especially if it is intensive in terms of memory, and some other instructions not related to memory at all. For example, what kind of instructions you are aware of that does not require any variable from the memory? Does not do add, does not do multiplication, does not do any kind of mathematical operation. Transpose. Is it assembly instruction? They are very close, but give me an example. Assignment? Yes, I think so. I think so. And this is also related to branch instructions as well. Branch if equal to 0 or less than 0, all those instructions do not require any type of memory or data coming to the memory, okay? So that's why we take the average number of misses per instruction. And also we are going a bit more advanced now with the concept of miss rate. It's no longer just fetching a data from the main memory. And you remember that number? What was the penalty you pay to access the main memory? What was the time required to move data from the main memory? 50 to 100 nanosecond. 50 to 100 nanosecond from the DRAM, right? Now it's no longer that time only. We have to consider really the miss and hit rate. Hit time plus the miss rate, which we calculate over there, times miss penalty. What is the miss penalty? The time we just discussed. For every miss you're going to have, you're going to pay penalty, which is the time to access the next level in the hierarchy. Okay. We will see that in practical. We will take a lot of examples. I will give you the numbers for certain CPU, certain caches, and we are going to calculate the total time for a program together. Okay? Yes, yes. For every request, you are going to calculate that. No, now what we have here, the average. Okay, that's the average. For total, what is the total number of accesses, the hit and miss? Same as we did over there. We didn't have any specific instruction when we calculated, right? We just count in total how many times we request the memory to give us data, how many time of them we fail to get that data directly from the next level of cache. Okay, we will see that in detail, but here we are gradually increasing the knowledge. Okay, now what could cause a miss? Why we would have a miss in any of the caches?
Cache is very small, so we basically keep the instant data.
Excellent. Excellent. So the cache simply is full, right? Then we need to replace the data, right? We need to bring more updated data. Thanks. But the first trivial reason for having a miss is the cache is empty. We just turn on the computer, right? No more data. So that is the most trivial one, compulsory, first time to fetch a block. Just totally empty, and we need to bring that block of data. The second thing, what your colleague said, the capacity is already full, and we need to get more data, so we need to replace, flush some of those data and bring in more updated data. The third one is the conflict. The capacity is not longer a problem. We already have space in the cache, but we have a conflict. What does it mean? We will see that even if we have an empty cache, right, it's divided into certain things, right? And when we map a piece of data, it's always going to map to certain location in the cache. It doesn't matter if it's full or empty. So whatever we have that piece of data, we map it, for example, to here. That one was full. That particular location was full. So now we need to replace it. And this is what we mean by conflict. The entire cache is still empty. Only this piece is full. And that new piece of data is also mapped to the same location. And now we have a conflict, so we need to replace them, although the entire cache is still empty. Hopefully now, when we calculate, you don't consider only these numbers. We have the concept of miss and hit rate. Okay? We will see what else we are going to add to that equation as we move with the lecture. Okay. Now, we saw an example in Tesla cars. We have only single level of cache, right? A huge one, actually, 32 megabyte. It's not kilo, right? It's not 1 kilo even. Why not just adding L4 cache? And everyone would be happy. So instead of going to the main memory, which is 100 nanosecond, we can have something in between like 10 nanosecond, which is level 2 cache or level 3, and 100 in the main memory. We could have something in between, right? And then we can reduce more the execution time. This is true. Having more level of caches is going to improve the things. And let's see, this is one of the real processors, one of the real CPU in i7 group. So in the i7 family, we have a lot of those different CPUs. Although it says i7, all of them i7, but each of them is different architecture. Or at least the common architecture is there, but different specs, for example. This specific processor has L4 cache. The rest having up to L3 cache. Okay? The size of the L4 cache is 128 megabyte. 128 megabyte. And this number is really important because we are going to see an outlier in the plot. Okay, 128 megabytes. Now those, the data access range. I'm going to access this amount of data to the CPU, right? What we have here, the latency, right? And we can see almost they perform exactly the same, regardless the amount of data that we are requesting. Now, once we hit the 128 over here, okay, we start seeing an outlier in the performance. The latency become much better with L4 cache, right? You can see the red plot is dropping until we arrive to the capacity of the L4 cache, which is something in here. The moment we hit this point, what will happen? They all perform the same again, or almost the same. Why is that? Because now L4 is already full. We already requested an amount of data that's equivalent to the capacity of the cache. So it's already full, and doesn't matter what kind of L4 cache you have, you still need to go back to the main memory and get back more data. That's why all these three types of processors perform now exactly the same. So what is this telling us? Even if you have more level of caches, is not necessarily always the best. It's not necessarily always to be your program faster. Why? We can see that the performance is exactly the same, and also in this area is exactly the same. It's only different when we are dealing with large amount of data that is exceeding the L3 cache. We exceed already the L3 cache, now we go to the main memory. But when we have L4, we stop, no, don't go to the main memory, go to the L4 first, bring more data, and then go back to the CPU. So only in that particular case, we have a best performance, and this is, we can consider as a niche. Just one case out of too many cases, right? Who's going to see the impact? Basically, people dealing with memory-intensive workload, okay? Who needs really amount of data to be exactly present now in the caches. That's equivalent to 128 megabytes. That's a huge amount of data that's needed to be exist now within certain clock cycles. And also, we said that the problem about caches, they are fast, but what is the problem with caches? More expensive. Excellent. Now, both of them are i7. Okay. One of them with L4 cache. Remember, all these caches are on chip. So it's inside the CPU. It's no off chip. Okay. So when you buy the CPU, you have to look on these specs. Now, this one without, this one with, what is the price difference? Almost double, right? So this is a very important metric. Do you want to pay double for something benefiting you only in one case out of maybe a million of cases or thousands of cases, right? That is the right question to ask. So you could say always, oh no, the most expensive one is the better, right? Let's go for the most expensive. But when you look at the performance, no difference at all. You pay double price or half price, no performance difference around that. All right. So now this is a very nice topic related to optimization. And this is really hot topic for research. There are a lot of research paper about this. How you could optimize the performance of the CPU without really changing the hardware. What does that mean? One way of doing that, which is the multi-threaded performance, right? You have in cores, and each core have many threads. So you can redesign your program without changing the hardware. Hardware is still there. You change your program to be multi-threaded, right? And then each of those threads will handle, for example, certain aspect of the for loop. You have 100 times to iterate over the same thing. So you split it into multiple processes, and each process will be handled by different thread, for example. And then you scatter this information, you gather it back, and then you have the for loop ready for you, right? However, there are other ways of optimization. For example, speculative execution. What does it mean? And why we call it speculative? It means you do something that you might not need. You do something that you might not need. Sounds like a waste, right? However, sometimes really important to do so. Let's see an example to understand the concept. One important example of that, branch prediction. Branch prediction. What does it mean? How many of you use if else in their program? It's kind of impossible to see anyone is not using if else, right? Right. So if it is true, you achieve the things in between, right? If not, you go somewhere else. Now think about this code as an assembly code, right? So you do instructions, you try to execute them, but then you arrive to the statement and you cannot execute it, so there's a variable and you need to wait until you execute that variable, and then you can decide whether you want to continue or jump to something else, right? Now waiting for that instruction to be executed, that's a waste of cycles. So one way of doing so, you could predict, you could assume something that the program might not need this block at all, the else, because it's going to achieve that block anyway. It's going to execute that. Now, what if my assumption was wrong? I'm going to lose whatever I executed there. But anyway, the CPU was going to wait until that instruction to be executed to decide whether to continue here or move to the next block, right? So anyway, there was a waste of time just stall, which is doing nothing, or me trying to predict where to continue and execute something that might not be needed. Let's see an example. Here we have a piece of assembly code. Right? We start with the first instruction, loading some data, and then do some addition, right? So we are now at the PC. What is a PC? Program counter, right? What is the program counter? Excellent. So we have like an arrow over here pointing to that instruction. Every time we read one instruction, we move to the next instruction, right? Now, how we know where we are now? We already have a pointer pointing to the instruction that we currently have. And every time we move from one instruction to another, we add to the PC value 4 bytes. Why we add 4 bytes? Excellent. That's the size of the instruction. That's the size of the instruction. So it makes sense. We read one instruction, it means 4 bytes. So we already take that out from the program. We move by 4 bytes. Every time we jump, 4 bytes, okay? So now we execute the first one. So we see the orange color. This is fetch, decode, execute, and then do some memory, write back, right? This is the cycle of the CPU. Any CPU has to do fetch, means take the instruction from the memory. Decode it, mean to know where are the variables, what does it mean for the instruction, and then execute it based on the instruction. And then if there is a memory to be written back, we execute that in the cycle. Now we execute the green one, fetch, decode, execute, and then probably memory execute back or write back. And then we start with the third instruction. The third instruction is what? The third instruction is branch if 0. It means if we add those two variables and the result is 0, we have to branch to this address, which is 1. which means go to the first instruction. If it is not 0, continue with the gray color, right? Now, if we want to wait for that instruction to be executed, we have to wait until we get the result from here. So we already know that whether the result was 0 or not, right? So we cannot start fetching the instruction, for example, from here, because the result is not ready. So the result will be ready only in here. So that's why we start after some time, after we wait until the end of the pipeline, and then we start fetch, decode, execute, and then we know at this point where to jump. Then we already decide that we need to start with the gray color, the yellow, orange, and so on. Now, with the branch prediction, what we do basically is that we predict the moment we start with this instruction. It's already branch prediction, but we don't need to wait until we get the result because we are predicting something, right? And then we could execute directly after that without waiting for all cycles to be completed. And then the amount of time we save is about 4 clock cycles. We didn't play with the hardware, right? We didn't play with the caches. We didn't play with the CPU. And that was a good practice on how we could improve the execution, although the data might not be ready currently. So there are a lot of other ways. Yes, please. Excellent. What will happen? So that's an example. That could be a case, right? But could be also correct. Could be wrong, and we trash all the calculation, and we go back to the branch, and we branch the correct one, for example, right? However, you are anyway 1, 2, 3, 4, right? There are 4 cycles of stall, right? So the amount of time needed to do the prediction might be around that time. So either you save that stall and you process 4 clock cycle. However, the prediction is not executing only that instruction, but also continue with the rest of instructions. So you save 4 clock cycle, but at the end, you already execute the entire program. So even if it was wrong, you might lose that 4 clock cycle that you save, right? And you go back to the branch instruction, and then execute it again, and then jump to somewhere else. That's why one of the optimization that you can do in the compiler, you have an if and else, right? If you know most of the cases based on the data that will have that if statement true, okay, then the compiler will keep the code as is. If most of the probability, the else statement will be true, and that one will be false, the compiler will switch those for you. We'll make this as if and this as else. This is going to save a lot of execution time, because instead of checking this and decide to do branch over here or not, to jump to another instruction or not, right? Now you have this ready, the block is there. And then when you do speculative execution, you can guess it most of the time correct, because most of the time you are here and you don't need to jump. This will be your if statement. So there should be a lot of testing in order to guess what would be most of the time executing this or that, and whether your branch or jumping would be a correct jump or not. But that's a valid concern, and there are a lot of research on that particular point. What if the branch prediction I did was wrong? What could be? And probably I think we have 3 or 4 papers around that topic in the paper list. All right, so let's see now mapping the data to the cache. We have a clear example, very simple one. Assume this is the DRAM, this is the cache. Normal DRAM is much bigger than the cache. Okay, so we have here about 4 spaces only to store data. Now we have very long address because this is very large space, right? Starting from 0, 0 all the way to 1, 1. Here we have only 2 bits for the address. One way to do the mapping is just to consider either the LSB or the MSB. Do you still remember those terms? LSB and the MSB. Least significant bits. This is, remember, bits, not a byte, although it's uppercase. And most significant bit. These are the least significant bit, which are the bits starting from the right side, the MSB from left side, okay? So in this example, we consider only the first 2 bits in the LSB, least significant bits. And we map the data based on that address. Anything coming from the DRAM with the address 000, we always consider the first 2 bits, and we map them always to the first block. So now anything starting with 2 zeros in this column and this, right? For example, this one will always be mapped to the first block, regardless the cache is full or not. Okay? And anything ending with 1, 1 will always go to the blue one. But we have a problem here. What is it? Now we map, for example, let's pick one. Which one you want to pick? Pick a color. The red. Okay, want to map the red. We start with this one. Oh, there is 1 0. Okay, let's map it to here. Okay, excellent. Now let's pick the other red. Oh, it starts also with 1 0. Then we should map it to the exact same place, right? But now we don't know. There are 2 blocks with 2 different addresses, but we don't know whether the one we have in the cache is which one of them. Is it the first one in the DRAM or the second one? Why is this important? It's important for deducting. That's one thing. And also, we want to know whether it's a miss or hit, right? We visit the cache. We wanted that piece of data, but there are 2 copies in here. There's 1 copy. Which one of them I do have, right? What if what I have is a miss, is the wrong one? So that's why we add what we call a tag. A tag is where we store the rest of the address, right? So we store some bits in the LSB, but we also store the rest of the address. Why this is important? Because we still need to calculate the entire address to know whether that block is something in here or somewhere else, right? So remember the process. The cache is much smaller than the DRAM. That's why we consider only portion of the address rather than the entire address. But we still store the rest of the address because we want to know whether that block we have in the cache is exactly the same thing we are looking for, or it was just a miss and we need really to fetch back another block. This is what we call as direct mapped data to the cache, okay? And that's what we call as a direct map. Now, what if all the time I'm moving the red one? All the time I'm moving the red and somewhere else, and also this one. So here, the red one, we have the 1 and 0, right? Will go always to the same place. And this one will go always to the same place. So I have a lot of spaces in the cache, but always I'm targeting the exact same position in the cache, right? I'm trying to replace it. Although I have many other spaces, but I'm always targeting certain location to replace with data. So they invent a new policy to map the data from the DRAM to the cache to solve that issue, which is set associative cache. We said instead of mapping a data to the same location, now let's make that location as a part of a set of location. Instead of always mapping that block to single location, now I have 10 locations, 10 options for the same block with the same address, exactly same address. I have many options. Normally, it's multiple of 2. So we choose the size of the set to be 2, 4, 8, and so on. Each memory block can be placed in any cache line within a specific set. Place block into cache in any location within its set determined by the address. And you can know that exactly where to place it by use the modulus sign. So the block address, which is the LSB, right? modulus the number of sets in the cache. Let's see an example better than the text. Of course, accommodates conflict better because this is the main problem. We have the cache. One of the location always was a target, and we need to place the data over there. It's already full. Replace, replace, and so on. So now when we're increasing the capacity of the set, we are reducing the number of conflicts. But more complex, why? Let's see why. This is what we explained just now, the direct map, right? Each block go to a certain single location. There is no other option. Based on the LSB, we choose this address or this or that. Now in here, this one is considered as 0, 0, right? However, it's two options. Either we fit it here or fit it there. So if the LSB, 2 zeros, then we go to the set 0. We go to the set 0. However, when we go to the set 0, we have two ways to map the data. Either map it to the first location or to the second location. Okay? Likewise, when we have the LSB as 0, 1. Now, supposed to go to the second set. How many ways we have to map it? We have two ways, right? Either to this location or that location. Now, even if the first location is full, we can fit the block in the second location and we don't have any conflict anymore, right? However, if the two are full, now we have a conflict. So that's why we have multiple options to consider. That's why we call it way or a set associative cache. How many sets you want to divide your cache? So here, two-way, what does it mean? What are the options within a set I can map a data? And the sets mean how many groups should I divide my cache? Okay. I could consider the 8-way, for example, one set. One set means the whole cache is one group, the whole cache. And if the size of the cache is 8 blocks, then I have, for any block, 8 ways to map it. I can map it anywhere. I no longer rely on the address, because the entire cache is single set. Then I have 8 ways of doing that. If I do so, then I call it fully associative cache, because it's full ways, full of ways, basically. So I can map it to any of those ways wherever I want to do. Now, which one of them is practically used in any of the CPU you have, for example, i7, i9? Which one is used? What do you think? Does it make sense to have the entire cache as one set, one group? I can place the data anywhere I want. Why it doesn't make sense? Think about the 32 megabyte in the Tesla cars. 32 megabyte. It means the space is huge to place the block wherever I want. How I could fetch it back? How I could know that this block exists in that location? Then the complexity becomes really huge. So most of the CPUs you currently have are using the n-way associative caches. So you could specify that number, 8, 16, for example, 32. So I have as assignment for you, please go back home and check those things also for this exact same CPU that you have. So now you'll check the CPU, the clock, okay? How many references issued by the core per clock, and what is the caches you have? Do you have L4 cache? Do you have L3, L2, L1? And what is the size of these? And what kind of mapping algorithm used in there? Is it 8, 16, 4, 2 ways of associative cache or so? Okay, all this information are publicly available, so you'll find them. That's not graded. That's for your curiosity. I know you are curious. You want to know all this information. And we will continue with the next lecture starting from here. Okay? Do you have any question? I still have some chocolate. This side is very sleeping this time. So please, next time, try to participate. We have the aircon, I think it's off, right? We'll try to have it next time fixed. All right, thank you so much.